All right, let's talk about data. There's this one question that pops up all the time, no matter what you're working on. How much is enough? It sounds so simple, right? But the answer, well, it's way more interesting than you might think. Today, we're diving into the central limit theorem to figure out when we can finally say, okay, that's enough data.
It's this nagging feeling, isn't it? We all just kind of know that more data is better. But how much more? Is there a magic number? A finish line where we can stop collecting and actually be confident in what we found? That's the big mystery we're going to solve.
So to even begin to answer that, we've got to start with a concept that's, well, it's kind of like the one magic trick at the heart of all statistics. It's this amazing rule that lets us find order in chaos. I want you to picture one of those Plinko games, you know? You drop a puck, it bounces left, right, totally random. But what happens if you drop thousands of them? What do you see at the bottom? Bam! A perfect, beautiful bell curve. That's not an accident. That's the whole idea behind the central limit theorem. If you average out a bunch of random stuff, it almost always settles into this predictable bell shape.
Okay, so here's the more formal textbook version. What it's really saying is if you take a bunch of samples from any population, it doesn't matter what it looks like, and you average those samples, the distribution of those averages is going to look like a bell curve. And the incredible part, the part that makes it so powerful, is that last bit, regardless of the underlying distribution. It's the foundation for so much of modern stats.
So that sounds amazing, right? A universal rule? But, and this is a huge but, there's a catch. The theorem is fantastic, but it's got this one glaring blind spot. It tells us where we're going, but it doesn't tell us how long it's going to take to get there.
And this is exactly where things get tricky. The paper we're digging into today just puts it perfectly. The theorem promises this beautiful bell curve destination, but it's totally silent on how much data you actually need. What does a large number even mean in the real world?
Okay, so let's get real. Let's look at some actual data. U.S. family incomes. And whoa, that is not a bell curve. Not even close. You can see it's all bunched up on the left, with this super long tail stretching out to the right for the high earners. If we just assume our nice neat bell curve applies here, we are heading for big trouble.
And how big is that trouble? Well, the paper found that if you just use the standard central limit theorem to predict the top 0.5% of incomes, you'd be off by nearly 400%. That's not just a little rounding error, that's a massive, fundamentally wrong conclusion. Clearly, the basic theorem just isn't enough here.
So, what went wrong? Why did our magic trick fail so spectacularly? The answer isn't that the theorem is broken, it's that the specific shape of our income data is, well, let's just say it's got some personality. Let's take a look. Meet the two main culprits, the troublemakers if you will, skewness and kurtosis. Skewness is just a measure of how lopsided or asymmetrical the data is, and our income data is very lopsided. And then there's kurtosis. Think of this as fat tails. It tells you if you have way more extreme outliers than a perfect bell curve would expect. Our income data has plenty of both.
Okay, so if skewness and kurtosis are the villains of our story, we need a hero. We need a better tool that can handle this messy, real-world data. And luckily, a couple of mathematicians came up with one over a century ago that does just that. It's called the Edgeworth expansion. And yeah, I know, the name sounds super intimidating, but don't worry about that. The best way to think about it is as the central limit theorem version 2.0. It's not a replacement, it's a brilliant upgrade.
So how does this upgrade actually work? It's really elegant. You start with the basic, simple bell curve. Then you add a clever mathematical tweak to account for the lopsidedness, for the skewness. Then you add another tweak to account for those fat tails, for the kurtosis. It builds a more perfect model, piece by piece.
And check this out. This is the payoff. The red dotted line, that's the basic bell curve. You can see it's a pretty terrible fit for the blue bars of our actual data. But now, look at that black dotted line. That's our corrected formula. It's practically hugging the real data. It absolutely nails it. This right here is our aha moment. So what does this mean? We've got this super-powered new tool that gives us incredible precision. So what can we actually do with it? This is where we move from cool theory to practical, real-world answers.
It lets us do this. We can finally answer our big question. For that skewed income data, if we say, okay, I need to be 99% certain that my error is less than 1%, bam, the formula tells us we need a sample size of 90.
Want to get even more precise? Down to a 0.1% error? You're going to need over 5,000 samples. For the first time, we have a clear, precise roadmap.
This 3D plot from the paper is such a great way to see what's happening. That vertical axis going up, that's the error, and the axis going back is our sample size. See those big, scary red and yellow waves on the left? That's all the error when you have a small sample size. But as you collect more and more data, moving to the right, see how it all flattens out into that calm, purple sea of accuracy? That's where we want to be.
Okay, so that income data makes sense. But now for something completely different and honestly even more surprising. Let's talk about roulette.
This graph shows your chances of being profitable if you just keep betting on the same single number over and over again. And what is going on here? This is so weird. Your chance of winning doesn't just go down. It oscillates. It jumps up and down like crazy. At 35 plays, your odds are over 60%. But just one more play at 36 and they plummet. It's because the payouts happen in these fixed, chunky steps, what statisticians call a lattice. And now, this is the mic drop. Remember our corrected formula? When we use a version of it that's built for this kind of chunky lattice data, look what it does. The black dotted line doesn't just smooth things out. It predicts every single peak and every single valley of those bizarre waves with stunning accuracy. It perfectly explains this completely counterintuitive behavior. It's just, wow.
So what we've seen is that the simple bell curve can be a trap, but with the right tools, we can get an almost spooky level of precision. And that leaves us with one big question to think about. In a world that is absolutely swimming in data, where else are we trusting the simple approximation without stopping to ask, is it really enough?